Today we're going to be discussing the analysis that Plug Power has performed on the implications associated with the conceptual three pillars for the hydrogen production tax credit that's part of the Inflation Reduction Act. I'm Tim Cortez, the Chief Technology Officer at Plug Power.
And I'm Jerry Cahill, Vice President of Finance and Finance Leader of Plug's Energy business.
So let's begin by providing a high-level summary of the results from our study, then we'll get into the details. The concept of the three pillars that are associated with the hydrogen production tax credit have implications that Plug really needed to understand, and that's the purpose of our analysis. If we look at each one of them individually, we'll start with additionality, and it makes renewable power a value chain control point and limits business models. It also has the impact of reducing the benefits of green hydrogen as a source of power flexibility. There are also potential delays in the green hydrogen project development by up to 5 years or longer. And it also presents the potential for the reduction of 200,000 potential jobs that could have been realized, and also the reduction of carbon abatement by about 50%. If we think about the hourly time matching piece, there are increases associated with the production of hydrogen by about $1.30 per kilogram. Not only that, hourly time matching is not yet widely available in all parts of the country, which could also delay deployment. It also has the potential to reduce green hydrogen investment by 65% by 2032, 90% of gross jobs through 2035, green hydrogen demand of 75% by 2040, and the opportunity to get the emissions needed by about 540 million tons of CO2 equivalent of greenhouse gases and 4.2 megagrams per meter squared of particulate matter by 2040. Lastly, strict local geographic matching has the potential for increasing green hydrogen production costs by about $1 per kilogram. In addition to that, it creates regional winners and losers. Regions that have a high abundance of renewable energies are winners. Those that don't become losers. And that's explicitly counterproductive to the federal program, particularly the DOE hydrogen hubs. And lastly, it inflates the logistics cost and distribution costs for hydrogen to the end user applications. What's really important is if you now do a combination of hourly time matching and strict local geographic matching, you can get to the point where the cost is higher than the actual tax credit, which will cause many potential hydrogen producers to opt out altogether. But what's most important is that additionality, time matching, and regionality are not included in the legislative language, any legislative intent, or any colloquies associated with the 45V production tax credit. The intent of the production tax credit was to rapidly scale the hydrogen production. The three pillars are not within the legislative intent. It's really important to understand the context and why we did this study. The hydrogen production tax credit that's part of the Inflation Reduction Act is really put in place to be able to drive scale and to be able to improve decarbonization, drive job creation, improve energy resiliency and national security. In the next few months, the implementation of the regulations for the PTC will be finalized, and it was critical for Plug to understand how those potential regulations could impact the industry. So the objective was really to develop the scenarios and the models to understand the implementation within the hydrogen production tax credit. Understanding those implications were key to understand what could happen if these are implemented in a strict manner. So we really needed to understand and determine the gross impacts to the green hydrogen economy investments, to gross jobs, both direct and indirect, and lastly, the gross societal emissions impact, including greenhouse gas emissions and particulate matter. On to the analysis and the importance of understanding the sources of the data that was used in our analysis. It was really important to us that the analysis leveraged existing public market data, as well as Plug's industrial knowledge. So if you look at the slide, you can see that there's many sources of existing data that we used. The National Hydrogen Strategy and Roadmap, DOE's Pathway to Commercial Liftoff report, as well as the Hydrogen Council's Global Hydrogen Flow report. In addition, the public data that we use was existing data that's available to anybody to view. Information like from the GREET model for Argonne Labs, for example. NREL's solar and wind capital costs information, but also information from companies like Air Products that had public announcements of their new facilities. But what's really key to our analysis is that we also integrated Plug's industrial knowledge of what we're doing and how we're building out the hydrogen economy. We used the information from the build-out of our existing facilities and our plants. We used information from other models and other work that we did in terms of looking at jobs in the hydrogen economy. These are all critical aspects to ensure that we use public information and Plug's extensive knowledge in terms of how we're building these plants. The next several slides will be focused on the first concept of the three pillars, which is known as additionality. So the impacts of additionality go well beyond just project level economics. What we're seeing and what we understand is that there could be a 5-year delay due to the deployment of renewables that could impact the green hydrogen value chain. Additionality also possesses the difficulties in tracking and what truly is additional versus what would have just naturally occurred. It also makes renewable power and the value chain a control point that really will drive costs up at the end point. Fourth, it limits business models that could reduce decarbonization cost, which is limiting the potential system cost savings. There's also the potential to reduce system benefits of green hydrogen as a source of power flexibility in the network. Some other considerations is that new renewable sources would be driven and will be driven by market demands regardless. There's significant new capacity being expected to come online as market demands happen. In addition, the required energy capability for the green hydrogen economy is small compared to the renewable energy pipeline, which it actually will amount to less than 3% of the potential capacity of the renewable coming online. Many policies are already driving new clean energy demand and do not require additionality. An example of that is the EPA's EO 14057, which doesn't even include any form of additionality associated with that legislation. If we directly tie green hydrogen production to new renewable sources that are in the queue and have not yet come online, there will be significant delays in deployment. What the renewable projects are facing today is at least a 5-year plus waiting time. That's the time from interconnection queue request to commercial operations. And that can have a significant impact on the clean hydrogen production if those are directly connected to each other. Imposing those current 5-year delays and timelines have significant impacts, but they're already in the queue, and clean hydrogen would only represent about 1% of the renewable supply projected to be available in 2030. The 5-year or longer delays in bringing clean hydrogen to scale have a direct impact on the effectiveness and the intent of the legislation. If you delay 5 years the scale up of clean hydrogen production, you reduce the demand by approximately 60%. The implications of that are wide-reaching, including gross investments, which would be reduced by about 55% otherwise. In addition, the jobs that would have been created get reduced by approximately 40%. And the environmental impact in terms of potential abatement of greenhouse gases and particulate matter gets reduced by approximately 50% as well. So the key takeaway here is the delay in the development of green hydrogen projects means a delay in demand that's needed, which in turn turns into delays in investment, delays in jobs, and delays in the potential improvement in the environment. Those jobs could be as much as 250,000 jobs, and the reduced carbon abatement that we could potentially see gets reduced by approximately 50%. So now I'm going to turn it over to Jerry Cahill, and he's going to take you through the analysis of how hourly time matching and geographic matching impact the levelized cost of hydrogen, and how those cost increases impact the success of the legislation.
Thank you, Tim. I'd like to start by summarizing key differences in assumptions that other studies that have been published in the market are using as compared to our own studies. Hydrogen customers will require near 24/7 operations of hydrogen plants to fulfill their requirements. The other studies do not consider hour-to-hour requirements of hydrogen generation. They take a more annual view. Second, the capital required to meet those requirements, storage, excess electrolyzer stack capacity, and other CapEx and OpEx costs have been excluded from these other studies, and you'll see on the next slide some examples of those differences. Third, the cost of the electricity. In order to ensure hour-to-hour production and meeting those requirements to maximize the PTC requires excess energy cost, and you have to factor in the risk of not enough solar or wind generation during those particular hours. And fourth, these other models appear to be cherry picking. They're picking the projects that are most advantageous in the country and based upon their locality next to nearby renewable energy sources and those costs of electricity. However, in order to maintain an effective network, we will need hydrogen generation as an industry all over the country, including less desirable locations from a renewable perspective. Next, I'm going to give you more detail on the cost differences between studies that Plug has reviewed out in the market as compared to our own studies and our own observations as we're constructing our current hydrogen generation facilities. Studies that we've seen show in the green on our waterfall solely the cost of the electrolyzer stacks and the cost of electricity to run those. However, there's significant balance of plant required to build an entire hydrogen plant. There's also, usually, there is upstream an electric substation required, and that's significant CapEx that needs to be fully factored in. Some users of hydrogen will require liquid hydrogen. The liquefaction cost is not insignificant from a CapEx perspective. There's also will be markets that require delivered hydrogen. Transportation costs are not insignificant. And lastly, you need SG&A and other overhead to run these plants, and we believe that they've been excluded from the studies out in the market. So a fully loaded cost of hydrogen generation is significantly in excess of what may be out in the marketplace, thus requiring the PTC to equalize it. Also, the demand out in the industry, as independently published by the DOE, is significant and has not been factored into studies that we have seen out in the market. Next, I will review with you the difference between moving from more flexible policies to less flexible policies. To start, a flexible regional policy as compared to a less flexible, strict local geographic policy. The stricter policy will increase the cost of hydrogen by 40% by 2025 and 35% by 2030. From a time matching perspective, annual time matching as compared to hourly time matching. Hourly time matching will increase the cost of the industry by 55% in 25, 40% in 30. And then if you move both pillars to less flexible policies, there's a compounding effect to the degree of 115% increase in hydrogen in 25, which will more than offset the entire PTC. Thus, producers will opt out of the PTC because it will not be cost effective. And 80% in 2030. Another example as we move from flexible to less flexible policies. When we look at regional matching as compared to strict geographic matching, the cost of hydrogen will increase by as much as $1 per kilogram. And we project that the demand for hydrogen will be half, from 5 million tons a year to 2.5 million tons a year, requiring less jobs. A more flexible policy will create over 500,000 jobs, whereas less flexible from a geographic perspective would be half that. As we move from annual time matching to hourly time matching, we expect hourly time matching to be $1.30 per kilogram higher than annual time matching due to the cost of electricity and related CapEx required for storage assets. The demand will drop from 5 million tons to 1.2 million tons, and jobs will decrease from 500,000 to 50,000 jobs, a significant reduction of jobs and investment and carbon that could have been abated. And like I said earlier, there's a compounding effect. If we move to more restrictive policies on both perspectives from time matching and regionality, we expect a compounding $2.90 increase in the cost of hydrogen, again, approximating the entire value of the PTC in the first place. And again, a significant reduction in investment, jobs, and carbon emissions that could have been abated. Here we've shown example sites around the country where we are modeling out the cost of hydrogen production. We've used Georgia, where there are scarce renewable energy assets today. We've used Texas, where there are abundant renewable energy, both wind and solar. And use California, where there is abundant solar, however not sufficient complementary wind assets. And in all cases, in the near term, 2023 and 2025, we see a significant increase in costs to meet more restrictive requirements, approximating $3 or more per kilogram, again, in excess of the PTC value, individually and in the average. And even in 2030, while it may be less than the PTC, it is still a significant cost, 50 to 60% of the PTC value. And lastly, we've shown all the markets where we believe hydrogen will be competitive due to the levelized cost of hydrogen as compared to the incumbent technology and the operational inputs to those technologies. With more flexible policies, in 2025, you'll see the green circles in the columns. In nearly all cases, hydrogen will be competitive and will help facilitate adoption of hydrogen as a fuel source and as an input industrial process, and decarbonize all those processes you see. However, as we move to more restrictive policies, both in time matching and in regionality, you see in 25 and in the outer years, 30 and 35, less green circles, meaning that the cost of hydrogen in the future will not be competitive in these particular markets.
In summary, the analysis that Plug has performed allows us to look at what is the impact of the implementation of the concept of the three pillars. First, the additionality requirement. That particular item alone has the potential of delaying and pushing out hydrogen projects by over 5 years, with the resultant being the loss or the delay of over 200,000 jobs. And in addition, the potential for abatement that gets missed of over 50%.
And as we demonstrated, more restrictive time matching policies and regionality policies will significantly increase the cost of hydrogen in the near term and negate the effects of the PTC. And it'll drive down demand for hydrogen. It'll drive down investment in projects, jobs, and the potential for abating carbon emissions.
And lastly, one of the main points that we made earlier today, additionality, strict hourly time matching, regionality are not part of the legislative language. They were not part of the legislative intent and were not part of any colloquies associated with the tax credit. It's really important to make sure we understand that distinction.
And thank you for listening to this important analysis.
Thank you.